Hi student, in today's lecture for chapter alkyl halide and aryl halide, we discuss intermediates, characteristics of various intermediates, reactive intermediates. As I told you, reactive intermediates are formed in multi-step reactions. Multi-step reactions are those reactions which completed in more than one steps. Basically, this intermediates form is a species between reactants and products. In some cases, this species can be isolated from reaction mixture. So let's start with free radicals. A free radical is electrically neutral. Carbon atom electrically neutral carbon atom containing species having odd number of electrons. Having odd number of electrons. It is electrically neutral carbon atom containing species having odd number of electrons. It is formed by homolytic cleavage of a bond. For example, we have any atom or group of atom bonded from this carbon atom, and during homolytic cleavage of this bond, electron pair of this bond get distributed equally between these bonded atoms. One of the electron will come along with C and one with this X. So this carbon containing species, which is electrically neutral, there is no net charge, having odd number of electrons. 6 electrons from these 3 bonds and 1 because of this lone pair of electrons. So this is called as free radical. Now let's come to the structure of free radical. Now in structure of free radical, carbon bearing odd electron is sp2 hybridized carbon atom. This carbon atom is sp2 hybridized carbon atom because it has 3 sigma bonds, 3 bond pair of electrons and no lone pair of electrons. This single electron remains in unhybrid p orbital. So we can represent that these are 3 sigma bond formed by this carbon atom, and this is its unhybrid p orbital. So here we can say this is vacant this is unhybridized p orbital having single electron. And these are sp2 hybrid orbitals. This is also sp2 hybrid orbital and this is also sp2 hybrid orbital. So we can say free radical is planar intermediate. It is trigonal planar. Trigonal planar in shape. Its shape is trigonal planar. Now remember one more thing, free radical is paramagnetic species. Paramagnetic species. Now paramagnetic species means species that is attracted by external magnetic field is called as paramagnetic species. Now, to be a paramagnetic species, it must have unpaired electron, at least one unpaired electron. So, in case of free radical, there is one unpaired electron. So it's all about structure of free radical. Next come to types of free radical. In types of free radical. Types of free radical depends on types of carbon atom from which this free radical is formed. So it depends on the types of this carbon atom. So free radical can be primary free radical. If this carbon atom is primary carbon atom and represented as RCH2 dot, it can be secondary free radical and represented as RCH dot R. Tertiary free radical represented by this representation. It can be allylic free radical if carbon that undergoes homolytic cleavage of its one of the bond is allylic carbon, then the free radical formed will be an allylic free radical. Now, allylic free radicals are of various category depending on. This is also an allylic free radical. This is also an allylic free radical. Now, free radical can be benzylic free radical. In benzylic free radical, single electron is present on benzylic carbon atom. So benzylic carbon atom can be of this type or it can be of this type or it can be of this type. So in this case, we call it as a primary benzylic. And this one is secondary benzylic. And this is tertiary benzylic. Similarly, this is primary allylic, secondary allylic, and tertiary allylic. So these are the various types of free radical. And there is one more. Vinylic free radical. In vinylic free radical, all are benzylic free radical. In vinylic free radical, single electron is present on vinylic carbon atom. And you know that vinylic carbon atom is carbon atom of carbon-carbon double bond. So this is vinylic free radical. This is also vinylic free radical. So depending on the type of this carbon atom, the free radical formed by homolytic cleavage of this bond can be primary free radical, secondary free radical, tertiary free radical, allylic free radical, benzylic free radicals, and vinylic free radicals. All these are the allylic free radical, and these three are the benzylic free radical, because further these can be primary, secondary, and tertiary free radicals. Now let's compare stability of free radical. Relative stability of free radicals. Relative stability of free radicals. Free radical is an electron deficient species because octet of carbon atom having odd electron is incomplete. It have only 7 electrons in its valence shell. So, presence of a substituent have effect on its stability. Stability of free radicals. So first of all, remember that presence of electron releasing group. Presence of electron releasing group increases stability of free radical. Presence of electron releasing group increases stability of free radical. The electron releasing group now can be represented as ERG. This electron releasing group can show electron releasing inductive effect, or it can show resonance effect. So any free radical having electron releasing group will be comparatively more stable. Now consider the simplest free radical. Simplest free radical is methyl free radical. This is the simplest free radical. Now, in other free radical, hydrogen atom of this methyl free radicals are displaced by some substituents. For example, in case of primary free radical, one of the hydrogen atom of methyl free radical is replaced by an alkyl group R, while in secondary free radical, 2 hydrogen atom of methyl free radical are removed by 2 alkyl groups, and in tertiary free radical, all of 3 hydrogen atoms are replaced by alkyl. R stand for R is an alkyl group. It can be methyl group, it can be ethyl group, and it can be phenyl group. So in this free radical, there is only one electron releasing group. Here there are two electron releasing group, and here there are three electron releasing groups. So as the number of electron releasing group increases, stability of free radical also increases. So that's why we can say 3-degree free radical is more stable than 2-degree free radical, that is more stable than 1-degree free radical, and that is more stable than methyl free radical. This is the order of stability of various types of alkyl free radicals. Order of stability of various types of alkyl free radicals. Now, if we consider allylic free radical and benzylic free radical, so note that allylic and benzylic free radicals are stabilized by resonance. Allylic and benzylic free radicals are stabilized by resonance. So, because of the possibility of resonance in these free radicals, their stability is more than that of alkyl radicals, alkyl free radicals. Now for allylic free radical, number of resonating structures, for example, depends on structure of allylic free radical. Now for this allylic free radical, only two resonating structures are possible. If this electron shift here for bond formation, then this electron will comes out here, and this pi bond will cleave homolytically. So, the result of this homolytic cleavage is displacement of this odd electron. There is one odd electron on this carbon atom and one odd electron on this carbon atom, so both of them overlap laterally to form a pi bond. So these two are the contributing structure of this allylic free radical. So the extent of electron deficiency in allylic free radical is less than alkyl free radical. Now, if we consider benzylic free radical, in benzylic free radical, the single electron or odd electron is in conjugation with multiple bonds. And because of its conjugation, this single electron can delocalize over. So if this electron pair shift here, then this electron pair will comes out. The single-headed fish hook arrow indicate the movement of only one electron, not the entire electron pair. Here there is no electron pair, so movement of only one electron. So here there will be double bond, here there will be single electron. We get a new resonating structure. Now, in next structure, this electron pair will shift here and this electron pair will comes out because of resonance, because of delocalization. Now in next structure, this electron pair further delocalize due to conjugation. And we will get one more resonating structure, and in next structure it further delocalize so that electron pair comes out, and so altogether 5 resonating structures are possible for benzylic free radical. So here we can say there is greater delocalization of electron, single electron. So greater is the delocalization of single electron, lesser will be electron deficiency. Because this deficiency of one electron is dispersed over many atoms. So effectively, deficiency per atom will get reduced and the stability of free radical will get increased. So now we can say out of allylic and benzylic free radical, benzylic free radical is more stable than allylic free radical. Yes, because of more number of resonating structures. Because of more number of resonating structures. So now in general we can say the decreasing order of stability of various free radical is in general decreasing order of stability of free radicals is as follows. So it is benzylic free radical is more stable than allylic free radical, that is more stable than 3-degree free radical, that is more stable than 2-degree free radical, that is more stable than 1-degree free radical, and that is more stable than CS3 free radical, methyl free radical. Now, there was one more free radical, vinylic free radical. In vinylic free radical, the single electron or odd electron is present on sp hybridized carbon atom. Now remember that hybridization state of carbon having odd electron in benzylic, allylic, tertiary, secondary, primary and methyl free radical is sp2. But in vinylic free radical it is sp because of there are only two sigma bonds. Because of there are only two sigma bonds. So, and you know that sp hybridized carbon is more electronegative than sp2 hybridized carbon. sp hybridized carbon is more electronegative than sp2 hybridized carbon. Deficiency on more electronegative atom is more destabilizing. Deficiency on more electronegative atom is more destabilizing factor. So that's why vinylic free radical is least stable in the order of stability. Vinylic free radical is least stable in the order of stability. So this is an important thing. You have to remember order of stability of various types of free radicals. Benzylic free radical is most stable because of greater extent of resonance. Then allylic, it is also stabilized by resonance. Then 3 degree, 2 degree and 1 degree are stabilized by presence of electron releasing substituent. It have maximum number of electron releasing substituent and it have minimum number of electron releasing substituent. There is no electron releasing substituent and no resonance. And in vinylic free radical, deficiency or odd electron is present on more electronegative carbon atom. Now let's try one question. Arrange the following free radicals in decreasing order of stability. In decreasing order of their relative stability. So we have this is the first free radical. These are some free radicals. We have to arrange them in the relative order of their stability. A, B, C, D and E. Now all of them are benzylic free radical. All of them are benzylic free radical. So to compare the relative stability, first of all see what is difference in their structure. Now you will notice that the substituent present on para position in benzylic free radical are different. So these substituents shows different types of electronic effects. These substituents may be electron releasing substituents, or these substituents may be electron withdrawing substituents. So if all of them are electron releasing substituent, then all these four will be more stable than this free radical, because here there is no substituent. If all these substituents are electron withdrawing substituent, then all of them will be less stable than this free radical, because electron releasing group increases the stability of free radical and electron withdrawing group decreases the stability of free radical. Electron releasing group increases the stability of free radical and electron withdrawing group decreases the stability of free radical. So first of all, identify the electronic effect shown by these substituents. So this CS3 shows electron releasing hyperconjugation effect. Electron releasing hyperconjugation effect. Yes, as I told you, whenever CS3 or other alkyl group bonded to double bonded carbon atom, it shows hyperconjugation. So now I can write in short form, that is H effect. So this CS3 shows H effect. Now if we consider this Cl, so this Cl shows minus I effect, because chlorine is more electronegative than carbon atom, and due to the presence of lone pair of electrons, it also shows plus R effect. But out of its minus I, that is electron withdrawing inductive effect, minus sign indicate that electron withdrawing, plus sign indicate that electron releasing. So out of electron withdrawing inductive effect and electron releasing resonance effect, its electron withdrawing inductive effect dominates over electron releasing resonance effect. This is the dominating effect of Cl. Yes, as I told you, whenever I and R effect, inductive and resonance effect, are in opposite direction, means one is electron releasing, another one is electron withdrawing, then resonance effect dominates over inductive effect, except for halogen. In case of halogen, their inductive effect dominates over resonance effect. Now if we consider NO2, electronegativity of nitrogen is more than that of carbon, and it is a group of more electronegative atoms, so it shows minus I effect. And whenever NO2 group is directly bonded to carbon-carbon double bond or directly bonded to benzene ring, also shows electron withdrawing resonance effect. So it shows electron withdrawing resonance effect. So it is withdrawing electrons from both of the effects. So it's a very strong electron withdrawing substituent. Now for OH, electronegativity of oxygen is more than that of carbon. So it shows minus I effect. And there are lone pair of electrons on this oxygen atom. So it also shows electron releasing resonance effect. So now you can remember that whenever OH group directly bonded to carbon-carbon double bond or directly bonded to benzene ring shows electron releasing resonance effect. So for this OH group, out of its electron withdrawing inductive effect and electron releasing resonance effect, its resonance effect dominates over inductive effect. So now we can compare. In this free radical, there is no substituent. So it can be a reference. It can be used for reference. Here there is an electron releasing substituent. So the stability of free radical B is more than that of A, because electron releasing substituent increases the stability of free radical. In C, dominating electronic effect of Cl is electron withdrawing effect. So the stability of free radical C is less than that of free radical A. In D, there is a stronger electron withdrawing substituent is present. The substituent withdraws electron strongly through inductive effect as well as through resonance effect. So the stability of D is much less than that of A, and it is also less than that of C. Now in case of E free radical, the substituent present shows electron releasing resonance effect. So electron releasing resonance effect is a comparatively stronger releasing effect. So now we can say free radical E is most stable due to the presence of electron releasing substituent. After E, it is the B due to the presence of electron releasing substituent. Here there is a no substituent. Here there are electron withdrawing substituent. So the free radical A is more stable. Free radical C and D are comparatively less stable. Out of C and D, stability of C is more than that of D, because here there is a weak electron withdrawing substituent and here there is a strong electron withdrawing substituent. So the stability of C is more than that of D. So this is the answer for this question. E free radical is most stable and D free radical is least stable. So now consider one more application of free radicals. Now the bond dissociation energy of CH bond dissociation energy of CH bond depends on stability of free radical form. It depends on stability of free radical form. Now, whenever we have to compare bond dissociation energy, we have to consider homolytic cleavage of the bond. Homolytic cleavage of bond for comparison of bond dissociation energy. So we can say bond dissociation energy of CH bond depends on stability of free radical form. So it is inversely proportional to stability of free radical formed. Greater is the stability of free radical form, lesser will be bond dissociation energy. So we learned one more important concept. Bond dissociation energy of CH bond inversely proportional to stability of free radical formed. Greater is the stability of free radical formed, lesser will be bond dissociation energy of CH bond. Lower is stability of free radical form, higher will be bond dissociation energy of CH bond. For example, we have this compound with various carbon-hydrogen bonds. Suppose this is first carbon-hydrogen bond, this is second carbon-hydrogen bond, this is third carbon-hydrogen bond, and this is fourth carbon-hydrogen bond. And we have to arrange all these four carbon-hydrogen bonds in the order of their bond dissociation energy. So first of all, identify structure of free radicals formed by cleavage of these bonds. So this is the structure of free radical that will form by the cleavage of first carbon-hydrogen bond. Now, this will be the structure of free radical formed by cleavage of second carbon-hydrogen bond. And this will be the structure of free radical that formed due to the cleavage of third carbon hydrogen bond. And this is the structure of free radical formed due to cleavage of fourth carbon hydrogen bond. So if we compare that, this is primary free radical. This is allylic free radical. This is vinylic free radical. And this is secondary free radical. 2-degree free radical. Yes, primary free radical, allylic free radical. If you look carefully, it is 3-degree allylic, right? 3-degree allylic. This is vinylic free radical, and this is just normal 2-degree free radical or secondary free radical. Now, order of their stability, you will notice that, let's say, this is 1 degree, this is allylic, this is vinylic, and this is 2 degree. Order of their stability is allylic free radical is more stable than 2-degree free radical. That is more stable than 1-degree free radical. And that is more stable than vinylic free radical. Yes, based on that general decreasing order of stability of various type of free radicals, we studied benzylic greater than allylic, greater than 3 degree, greater than 2 degree, greater than 1 degree, and greater than vinylic. So allylic free radical is most stable and it is formed by the cleavage of second CH bond. So bond dissociation energy of second CH bond is the lowest bond dissociation energy. And vinylic free radical is formed by the cleavage of third CH bond. So its bond dissociation energy is highest bond dissociation energy in this case. So now we can say order of bond dissociation energy for vinylic free radical is the least stable. So the bond dissociation energy of third CH bond is maximum, and after third it is primary free radical, that is the less stable. So its bond dissociation energy will be more. So first CH bond, then secondary free radical. So it is fourth CH bond, and finally allylic free radical is formed by the dissociation of second CH bond. Its stability is maximum, so its bond dissociation energy will be minimum among these four. So this is the decreasing order of bond dissociation energy of various CH bond in this example. So this is the application of free radicals. Mainly free radicals are formed whenever a reaction takes place in gas phase or at very high temperature. Formation of free radical takes place in following reaction. Following reactions of organic compounds takes place by free radical formation as intermediate. And here first is halogenation of alkane side chain halogenation of aromatic compounds third allylic halogenation of alkene fourth addition of HBr on carbon-carbon double bond, addition of HBr on carbon-carbon double bond in the presence of peroxide. So we can take one example, CH3 plus Cl2 in the presence of light to form CH3CH2Cl. This is the example for first reaction. This is toluene. When reacts with chlorine in the presence of light undergoes side chain halogenation, This is an alkene treated with chlorine in the presence of light or at high temperature. Undergoes allylic halogenation. The allylic hydrogen atom will get displaced by halogen atom, and this is the alkene that react with HBr in the presence of peroxide, form CH3, CH2, CH2Br. Addition of HBr will take place according to anti-Markovnikov rule, because the reaction proceeds by free radical formation. So these are the examples for these reactions. So remember, in all these reactions, there is a formation of free radical intermediate. So it's all about free radicals. its characteristics and application. In next section, we will discuss carbocation, its formation, its structure, its type, relative stability of various carbocations, and rearrangement of carbocations. So, okay student, so today I end my lecture here, and in next class we discuss carbocations.